All right, in math there are lots and lots of different types of functions that we're going to start exploring. In this section we're just going to look at what are some basic types of functions that we'll encounter, what are the domain and range of these functions, and what are some kind of key points that would be on these what we sometimes refer to as parent functions. Because these are all kind of the basic functions, and then there is a whole family of functions that will relate to this, and we'll look at how we can graph those using a technique called transformations in future sections. So, quite a few of these to get through, so let's get started. So the first one is one you should be very familiar with. This is a linear function. Now, a linear function is just going to be a line. So a line, it could be a line that slopes up, it could be a line that slopes down, it could be a flat line like this. So there are really not consistent key points on a line. This kind of really depends on the slope and the y-intercept. So in general, we don't really have key points for this one, but I do know the domain and range for a line is infinite because it will go forever in both directions, negative infinity to infinity, and it will go down to negative infinity to infinity. So that is always going to be true. Now for the rest, I'll be able to find some pretty easy key points that we can use as a basis for future stuff. So for a squaring function, we will have the same key points that we can start with. So what I'm going to do for the rest of these is I'm going to make a little table, and I'm just going to pick a couple x values. So I'm going to pick -1 and 0. These are very, very famous x values, and then I'm going to plug them into this function. So this is a squaring function. So if I square -1, -1 times -1 is 1, 0 squared is 0, and 1 squared is 1. So these are three ordered pairs that will be on the squaring graph. So if I plot this, 0, 0, 1, 1, -1, 1, the shape this makes is a parabola, some kind of U shape, something you probably studied in Algebra 2. So in general, the domain of this is going to be negative infinity to infinity because it's going to go, you can put any x in you want, negative, positive, 0, does not matter. Now the range is not going to be infinite because the range, the lowest this thing will go is a y of 0, and then it will go off to infinity. So it's going to be negative infinity to infinity, range of 0 to infinity. Because you can see this is my lowest point. Now a square root function is a little different because I can't plug any number I want into the square root function. I can't plug negative numbers because if you recall, I can't take the square root of -1. It is not a real number. So I'm going to pick a little different points for these x's. I'm going to pick 0, 1, and 4. Now the reason I pick 0, 1, and 4 is the square root of 0 is 0, the square root of 1 is 1, and the square root of 4 is 2. Now I could have picked 2, but then the square root of 2 is not very nice, so decide not to do those. So if I look at the graph of this, just plotting these points, 0, 0 is my first point, 1, 1, and then 4, 2. So this is going to kind of look like some kind of ramp. That's what a square root function looks like. So the domain and range of a square root function are a little different. I can't plug in any x. The smallest x I can plug in is 0, so it starts at 0 and goes to infinity. And the smallest y I can get is 0 and then goes to infinity. For our basic just square root function. Now again, I'll be able to change these eventually, make it have higher ranges and smaller domains and things like that. Okay, next let's look at the cube function. So if you have x cubed, this is a cube function because you're taking the x's to a third power. So I'm going to go back to my traditional -1, 0, 1, and I'll do that for the rest of these. I'll do -1, 0, 1 for all these values. So if I cube it, -1 to the third power is -1. -1 times -1 is 1, times -1 is -1. 0 to the third power is 0. 1 to the third power is 1. So if I plot these points, they will look kind of like a line to start with, but the cube has a distinct function shape. It looks like this, where it kind of snakes through these points. And you could graph any of these on Desmos to kind of see the generic shape. And then the domain of this, domain of cube function is nice because I can plug any number in and cube it. So that's negative infinity to infinity. and I can get any number out. So that's negative infinity to infinity for its range. Now, taking the cube root is really what number times itself 3 times will give me negative 1. It's negative 1. What number times itself 3 times will give me 0? It's 0. And what number times itself 3 times will give me 1? It's 1. So this is going to look something like this. So I'm going to have a point here in the middle, 1, 1, negative 1, 1. So it's going to look something like this. So for a cube root function, I can plug any x in I want, and I can get any y I want. So my domain and range are both infinite. Now for exponential functions are we have b to the x power. Now there's lots of exponential functions too. Y equals 2 to the x, y equals 3 to the x, y equals 4 to the x. These are all exponential functions. This is something we'll spend a lot of time on doing some applications of in the future. So if I pick my same values, negative 1, 0, 1. Now if I take b to the negative 1, if you recall, b to the negative 1, a negative exponent means you flip it. So I get 1 over b as my key point. B to the 0 is 1, and b to the 1 is just b. Now these would always obviously be dependent on what my b value was, what that base of that exponential is. Now, for the graph of this, what you'll see is you'll see a point here at negative 1, 1 over b, which is generally going to be here, 0, 1, and then 1b, and that could be anywhere depending on what b is. But it flattens out and then it takes off like this. This is what an exponential looks like. So of a basic exponential, there is any x you can plug in that you'd ever want, negative infinity to infinity, but the range is 0 to infinity because it doesn't go below 0, and it's a parenthesis because it never actually hits 0. It gets very, very close, but does not touch it. All right, so now let's look at a log graph. So a log graph is kind of different because in a log graph, you can't plug in any x. Log graphs are actually restricted to numbers that are positive. We'll talk about why later. So what I'll go ahead and put in here, I'll put in 1 over b, negative 1, 1, 0, and b1. Now b is going to be the base of the log, which is going to be a number here. So a lot of times you'll see a little b down here. It could be a number. It could be a 2, a 3, a 4, whatever. So what my graph is going to look like is, so I'm going to have 1, 0 as a point. I'll have a number here, and then I'll have one out here. This has a kind of a horizontal or vertical line that kind of breaks it apart. So this graph looks something like this. So the domain for a logarithmic function is 0 to infinity, not including 0. That's a parenthesis. And the range is everything. Now, a periodic function is one that's going to be kind of like a wave. It's going to go up and down and oscillate. So lots of things in our world oscillate. So sound waves, electricity, things like that have this kind of wave feature. So we'll see some periodic functions. Now, this is kind of an odd thing, but I'll put some key points on here for you, and we'll explain why these are. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Don't get too hung up on these right now. 0, 1, 0, negative 1, 0. Because what's going to happen on this axis, we have this axis divided in these weird increments of pi. It doesn't have to be pi. But what's going to happen is this thing is going to oscillate between these points. It's actually going to continue this pattern over and over again as some kind of wave. So the domain for a general sine or cosine or any kind of periodic wave is going to be negative infinity to infinity. But the range, this thing just keeps bouncing back and forth between negative 1 and 1. So we'll see some different applications of that. So some of these on the back are some different ones, some pretty tough ones. Logistic growth is a cool one, because logistic growth is actually one where you can see how things grow over time. A lot of infectious disease follows a logistic pattern. So the points on a logistic graph, these are going to be pretty weird. I can still pick up negative 1, 0, and 1, But for -1, the y value is 1 over 1 plus b. So whatever this b is typically a number, 2, 3. Now for 0, it's always 1/2. And then for 1, it is b over b plus 1. So whatever that base is, that's how you're going to do those points. So no stress about that. But what this graph is going to look like is it's going to look something like this, where it flattens out, it goes up, and then it flattens out like this. So this point would be 1/2, and it looks something like that. So the domain for this, it's going to go forever, -infinity to infinity, but the range, kind of odd, the range is bigger than 0, but less than 1, so just between 0 and 1. It's going to flatten out at the other ends. Reciprocal function is another one we have, so x and y. So I'll pick some points, -1, 0, 1, but if I flip those, I still get -0, 1. So this has a lot of the same points as them, but it's going to look something like this. It's these opposing curves. So the domain of this one's kind of bizarre. It's everything except 0, so it's -infinity to 0, 0 to infinity. And the range is the same, -infinity to 0 and 0 to infinity. So these key points we have are going to be important because those are going to be the ones that are going to take to actually make different types of the same graph. All right, finally, there's one more I did not put on your notes I'm going to have you add, so you can yell at me. That is an absolute value. It's a pretty important one, so it's a very easy one too. Some of these ones on the back are pretty obscure. We probably won't do those a lot. But an absolute value function is a pretty good one. It has an infinite domain, means you can plug in any x you want. Its range, however, as you will see on the graph, only goes from 0 to infinity. Now my key points, remember, for absolute value, it just makes numbers positive. So if I plug in -1, then the absolute value of -1 is 1 because it makes it positive. The absolute value of 0 is still 0. The absolute value of 1, already positive, stays positive. The graph is a pretty important one, so if I look at it, I have 0, 0, 1, 1, -1, -1, 1. So it looks like a V, something like that. So in this short video, we have literally seen about every type of mathematical relation that is in existence. And so we will obviously not be able to study all of these in the short time we have left together. But we will definitely look at some of the highlights, see how you can use these as you move forward.